first of all, welcome everyone. Thank you for being here at this LFDT Belgium meeting group. So we are organizing this from Bruges in Belgium. First, this was going to be an in-person meetup, but then we chose to pivot it to online. And actually that's great because now we have a much bigger reach. I'm really excited about the program for this evening because I believe that this topic is something very important. Blockchain technology has already matured a lot. There's lots of different flavors of blockchain. However, to have a broad adoption, to get to many real life use cases that go beyond the pool of the crypto believers, there's one aspect that really needs to be tackled, in our opinion, and that's privacy. Because in a world where so much of our life is digital, where AI systems might even become agents, there's a big need for trust. However, if privacy is not possible, then in business contexts or even in privacy regulation contexts, it just keeps stumbling. That's also the challenge we have at our applied research at West University Cyber 3 Lab. So 3 very exciting solutions or emerging solutions to tackle these privacy issues are actually going to be presented this evening. The first will be on decentralized identity, which will be presented by Renata Toktar from DSR Corporation. Next, there will be zero knowledge proofs cryptography, presented by Ruben De Smet from Vrije Universiteit Brussel, or in English, I think it's Free University of Brussels. And then later, last, we will have Peter Broadhurst from Kaleido that will be presenting on what I believe is a very exciting LFDT lab named Paladin, and that is for privacy on any EVM chain. Actually, I didn't need my 10 minutes at all. I think time is never a luxury. So I suggest we just get started, and Renata, the floor is yours.
Nice, thank you a lot. Hello, everyone. Hello, new people. Yes, I will be happy if you can ask any type of questions, but I'm not sure that during the presentation I will be able to read this, but I will try. Anyway, I think it will be time to answer for questions after the presentation. So today we will speak about, in my session, we will speak about decentralized identity. It is like digital identity, but more specific, and I will tell you why. So our goals for today here to make a small overview of self-sovereign identity and decentralized identity in general, understand some concepts and models, understand that it is not just like one direction, one tool or specification. It is a whole set, it is the whole market, the whole set of different technologies and tools. So summarize all of this different information about self-sovereign identity and speak a bit about discuss interoperability between different approaches and tools, because right now there are a lot, and there are a lot of people who are a bit scared of combining different technologies, partially because of technical part, partially because of reputation of some technologies. So we will start from the very beginning about self-sovereign identity. And after this, we'll discuss protocols, verifiable credentials formats, and verifiable data registers that can be blockchain, but in theory, not only. So to understand the current audience, and if I need to focus more or less on self-sovereign identity concepts in general, could you please send a message to our chat? If you already know something, then I will understand if I need to focus on this more or less. Thank you in advance. So a few words about me. I started working with blockchain technologies 9 years ago, and with my own startup. And after this, I found DSR, who were working with digital identity and distributed identity for many years. And that's how I started working on this from my favorite project, Hyperledger Indie. So I'm a bit sentimental. That's why I was leading and still leading in the Unbez initiative. So also I was in a core team, lead of team for Czech project from the start, and a lot of other projects that DSR was leading for last years. So, and why DSR wanted to tell about this? Because many years ago, we started working on Hyperledger Indie project like authors. And after this, there were a set of different projects that started from Indie. And there were like uncreds specifications, there were areas, RFCs. And now, of course, we are working a lot with OpenID for VC and with Open Wallet Foundation because of the new reality of the market. So we try to follow all technologies and understand all of them, having contribution to most of popular open source projects. So finally, about our goal, about SSI. Let me check. I can't see any pluses in our chat, so then you will know everything about SSI. I'm sorry if it will be too detailed. What we usually have using different websites, different services, we have accounts on every website. And we can't control them fully because your personal data stored on another server where you can't control it, where you can just like ask for removing this. In theory, they can answer to you or remove. You can check it, and all of this a bit uncomfortable and not good from the legal perspective also. So that's why self-sovereign identity, when you can control your identity. It is a bit close with an idea of authentication via authentication via existing accounts like Google or Facebook accounts, but still in that approach you have your personality allocated somewhere. But for self-sovereign identity, you are only one owner of your identity, of your documents, and no one can use them to pretend that it is you. So what is the concept here? Verifiable credentials that holder stores on their site, for example, on a mobile device, and provides to verifier only a proof of some fields of this credential, of existence of this credential, but holder doesn't send the whole verifiable credential. It is always a proof. It's the main idea. And another concept of self-sovereign identity is decentralized identifiers. It is a specific idea of having identifiers that can be unique for the whole internet, and where you define the place where this identifier is stored. And usually it is a place like verifiable data registry, for example, blockchain. I like the option with blockchain, but I know that right now there are a lot of different opinions and myths about blockchain. That's why it is not required to have blockchain here. But I like this option. So about the concept, so what is verifiable credentials? It is usual documents that we can see in electronic formats. It is something like passports, usual documents, but that you can receive it fast, secure, It's impossible to steal your documents and pretend you steal your passports and pretend that it is you. And this concept should be much more comfortable. And also it will be defined in European Union by EUDI, EDAS 2.0. Very soon it will be required in 2026. So we hope to see this on markets pretty soon. So just a few words about decentralized identifier that I mentioned, DID. The format of DID is like DID and method. So each method has its own specification with description of this method, and some unique identifier that will be unique for this DID method, or also it can be some namespace for pointing a specific place where you can find this document. And what it is not only identified, it's also a DID document with a set of different fields. Some kind of metadata, but with a lot of useful information like a set of public keys, how it's possible to use these public keys, controllers of this DID document of this entity, and for example, services, where you can mention some web resources, some endpoints that is also valid for your DID document, for example, for your organization. And these DID documents usually people store in the blockchain or another type of verifiable data registry, but that's people try to use all the time to have a history of all DID documents to make it possible and make it available all the time, to make it possible to verify a credential. For example, a verifier received a credential, and for validating this, you need to have a public key of an issuer all the time available. And it's better if it is available not on the verifier side, some web server, but somewhere in distributed in decentralized storage, where it's possible to read anytime, at any time. So in just a few words about concept, here we have three main roles. It is issuer, who creates a verifiable credential, issue credential, and send it to holder, but doesn't keep this information on their side. It actually would be useless because issuer can't make a proof, a presentation of this credential. So holder, who receive a verifiable credential and keeps it on their side, and after this can make a presentation for the third role, for verifier. So in this story, usually issuer has a DID documents with their public key, and also a schema of this document that is linked to this DID. So, and this data usually issuer stores in verifiable data registry. Holder doesn't have DID documents in verifiable data registry, so it is legal, but it is not required. And verifier also usually doesn't have their own DID document, so I think maybe it will be our future to have this record also on verifiable data registry side because of regulation. But from the clean concept, it is not required. Just verifier needs to read the data, like issuer data, from this registry. If we speak about the whole system and not only about flow, we can divide all applications for different layers because it is also it is a technology stack of low-level technologies like peer-to-peer communication protocol and like trust protocol applications. And from another point of view, it is also governments covered by government frameworks and by the law about all of these technologies. So I like to see this right now because 7 years ago it was like very nice dream, but it wasn't somewhere in government's frameworks. It wasn't legal. Now it is legal in most of places, in a lot of places, and in some countries it is already integrated to their government system. And let's look at different formats. Some of them maybe you've already heard. For example, verifiable credentials can be like just a JSON object, or can be a JSON LD object. What is the difference? The difference is in definition of the schema of these documents. So, like usual JSON LD, you have a link to each field, to each object. So it's very strict format. So also right now starts to be more popular BBS Plus and actually BBS Sharp also formats. It is also about JSON LD, but with BLS signatures. And so also it's possible to make it in the format of W3C credentials. I will tell about this a bit later. And another type of credential that was started with Hyperledger Indie project, this anonymous credentials. I like this format actually because of selective disclosure and predicates. Other formats have some kind of predicates, but only in unencrypted it's possible. By predicates, I mean that you can prove that you, for example, over 18 years old, but without disclosure of your real age. Or it also works with any other fields. And also the format that maybe you heard already, mobile driver license. It is some kind different here, but in general, it is still some kind of verifiable credential. So right now it is legal in few states of US, and so we hope to see this common in Europe pretty soon. Okay, we discussed formats of credentials, and now let's discuss protocols. Like credentials, it is some kind of, let's say, JSON objects or something like this that you need to issue. It's better to make it secure and also verify. So for making these processes, there are a few protocols. OpenID for VC that is right now in EUDI standard. It's possible to use any type of credential, and I think it is important because usually people think that OpenID works only, for example, with SD, GBT, WT, or with some specific formats that is like common. But actually, no. Even anonymous credential, it's possible to issue via OpenID for VC. So another kinds of protocols, it is DITCOM, and it is a bit old, but still actual, and it's possible to use it for ARES. ARES is a protocol for issuance, but DITCOM is a bit more generic, like OpenID, generic protocol for the transport layer. It can be interesting because it is very regular opinion that DITCOM works only with ARES. It is not the truth, but it is very close to the truth. And of course, mobile driver license protocol. For mobile driver licenses, it is separate, but for example, via OpenID for VC, it's also possible to issue a mobile driver license. W3C That is, in general, can be some kinds of additional metadata, like usual verifiable credentials that are covered by additional entity from W3C. So a few words about DID methods. There are a lot of DID methods, like hundreds of DID methods. And I can't say that one of them is better than another one. For example, I was working on DID Indy, DID Check, DID Hedera, and Ethereum, and a bit we're right now looking at DID but it doesn't mean that one of them is better. From my personal point of view, some of them, I mean, each daily method can work with for your specific task, for your requirements. And if you have some specific requirements, you need to find daily method that suits to your task instead of just using popular one. So, a few words about framework. We are a bit out of time, I think, because I still have a lot of slides. So how it's possible to start issuing verifiable credentials? One of the popular options right now is Kaleido framework, XRS framework from Open Wallet Foundation. And also there is a nice mobile application this was named Bifold based on Kaleido. So starting with OpenID for VC and ARES and unencrypted credentials, it's very easy to start with Kaleido. I can recommend you to play in this in your free time if you want to try it. So most of formats, it's like a nice trusted cryptography and very popular on the market and production already. So verifiable credential formats. Just a few words. We already saw a table with comparison of different types. So now let's speak about them a bit closer. Unencrypted. You see characteristic here. I want just to tell you some pros and cons from my point of view, because pros, of course, is predicates like older than 18. Selective disclosure, you can show just some fields. ZKP and anonymous revocation. So because revocation is always a tricky moment when you need to revoke a credential, you need to mention it. And it will be like obvious for everyone that this credential, your specific credential, is has been revoked, and it will not be anonymous. And this is the idea of anonymous credentials. Unpleasant moments in using unencrypted that it is not in UDI standard right now. And some people worry about its cryptography. I can say from my point of view that it is very absolutely trusted and it is absolutely normal, like CL signatures. But at the same time, I understand that if it is not popular cryptography, so it is enough not to use this. I think the next generation of unencrypted credentials we can see in BBS Plus credentials. So a few words about history. So we started with unencrypted from India project. It was in sovereign mainnet doesn't work right now, unfortunately. Just because of investment, actually, not because of technologies issues. And after this, it was a cryptography library from Indie Cryptography, like URSA, a new one, and areas RFCs for issuance process of unencrypted. W3C, I mentioned it a few times. It is serialization of formats of JSON and JSON LD. In fact, it is some kind of additional proof and additional metadata for credentials. And something, for example, like you can you should put a link to revocation list. So it's impossible to some place where it's possible to check if a credential is still valid. And from my point of view, it is like more standard format and more comfortable in a lot of cases. Guys asked me to tell a bit more about SDJWT, SDJWT also. It is selective disclosure for JWT, sorry. I think you heard about JWT. It is very popular right now. And the main difference here that you have, instead of payload, you have a list. I mean, of course, you also have a payload, but in JWT credential, you have and presentation. You have a list of disclosures. So it means that you have hash of each field in your presentation. And when someone wants to check this specific fields, for example, Alice wants to share only her name without her age, a verifier can, so Alice sends to a verifier like, my name is Alice. And verifier can take a hash, check hash of this value like name, Alice, and check that it exists, and this is the JWT. So it's possible to check that SDJ is correct, is valid. And also it's possible to check that inside this we have name Alice, hash of name Alice. And it will be enough. And in this case, verifier can't check the age of Alice. That was our goal, selective disclosure. So I will speed up. I feel that I have only a few minutes more. For example, it is an example of W3C verifiable credentials in JSON LD formats. And also there's a proof for this credential with this DCA signature. So just to understand how it looks in real world with real examples. So you have a credential with some specific fields, you have a proof, and you make a verifiable presentation for a verifier where you show a proof part and you show your credential. So why it's impossible to use it for verifier for someone else? It's because verifiable presentation is a one-time entity. And for example, here is a good example where it's possible to use zero knowledge proof, because we can show only right now on the specific stuff only for this person, and it's possible to use it somewhere else. Usually it also works with master keys, sign-in master key from verifiable credential from the issuer side. Too much specific information. I'm sorry for this. Exchange protocols areas, as we discussed, for unancred, but also possible to use for other credential types. For example, why not? JSON verifiable credentials are very easy to issue via any type of protocol. OpenID for verifiable credentials. I think you saw how OpenID in general Connect works. So here we just remove this line between issuer and verifier by authentication process here and here between other roles. So, and maybe a bit closer, issuance, you have OAuth authentication, OAuth 2 based authentication. And then issuer can issue a credential, using a token. So here it's also very good for JWT tokens, selective disclosure, SDJs. And verification process, here it is the name of for presentation. So it is also authentication. There are a few different possibilities of using verification, different types of verification. And after this, when you know your verifier, you can send a presentation of your credential, almost the same. So I think someone has to stop me because I have a lot of information about verifiable data registries, like blockchains. But I think we already have this topic today. I will not focus on this too much. I just want to say that there are a lot of them. Old, new, Ethereum-based, Cosmos SDK-based, for different types of credentials. But what is important from my point of view that as a lot of DID methods, you always can have can find a verifiable data registry, a blockchain that suits for your task. It can be permissioned, it can be open or closed, with different roles, with proof of stake, with different types of consensus protocol. For example, India was with RBFT. Cosmos has the nice X standard means. With Hedera, for example, it is Ethereum-based protocol. So mostly that's it. I also have a lot of information, but I will try to stop here. And I'm really interested in your questions.
Thank you so much, Renata. Because my intro was very short, you're still perfectly on time. So
Yeah.
also thanks for the nice overview. I think both for these knowledgeable, it was very detailed, but if you hear it for the first time, it's also possible to get the idea from scratch. So thanks a lot for this. Afterwards, this talk will also be on YouTube. So if you want to share it later with anyone, it will be possible. And just before you ended your presentation, a question came in the chat. So I suggest you can still answer this question before we go to the next topic. Yeah, thank you.
Yeah, sure. Thank you a lot. So I see a question about my preferences. I like it. So what's the question is what is technologies and best practices approaches to get started with SSI? And the question if it is depends on application. So I want to say that it is always depends on application. And from my point of view, it makes sense to start with some frameworks because I know, I mean, I am also one of these people who will implement in specific protocols, but starts with, for example, Creditas, maybe just being easier. And also, I recommend to start right now with Open ID for verifiable credentials, like one of the most popular protocols and one of the most flexible, actually. And maybe start with SD JOTs, like one of the best solution, and at the same time, it's like very easy. It's possible to understand just for, I don't know, for half of hour. There are no like difficult new cryptography, everything based on well-known elliptic curves, well-known cryptography. So you can play with this, take your time. So I hope that it will be interesting for you.
Thank you. And maybe one last question, and then I really need to stop this topic, even though it's very interesting. Do you see any barriers in adoption? And maybe to add to that, also, in the end, I see so many chains. Is it like with layer one blockchains that you're like forced to choose one ecosystem and that they are competing against each other, or can it move interoperable?
So answering for the first question about adoption, adoption in general of self-sovereign identity. Right now it is already in a regulation of Europe Union. It is some kind of regulation in the USA. So we see this a lot. One of the first country it was Canada. And also we see interest in this in Asia. And also like a successful story was a few years ago in Bhutan, where they fully implemented all electronic documents based on this. Of course, it is not like 1 day or 1 month or even 1 year story. But anyway, I think finally I work with this because I believe that it will be everywhere in a few years. Answering for the question about ledgers, I was working with half of them maybe on the market, and I like all of them because they're like my kids. I always try to have an approach like different ledgers for different goals. Like they should be absolutely different. For private networks, for people who want to play with cryptocurrency, for people who absolutely don't want to touch cryptocurrency at all. So from my point of view, right now I work a lot with Hedera because of this flexibility. I like Indie on Bezu because it is the next step of Indie, like my dreams. Because I like Indie. Checked is also good. So I can say that one of them is the best option, but you can choose your own preferences here.
Okay, thank you so much. And I heard a few times about zero knowledge proofs, so it's actually the perfect transition to learn all about this. So now I will give the floor to Ruben De Smet from the Free University of Brussels.
Thank you for the nice transition. Indeed, I completely agree that going from self-sovereign identities to zero knowledge proofs is a really nice transition. And I'll make a few references to the previous presentation because it's actually really interesting. So zero knowledge proofs. I'm Ruben from VUB. I've been a postdoc researcher for the past years, and I've spent the past 7 years, I think, working on privacy enhancing technologies, and zero knowledge proofs is one part of privacy enhancing technologies, right? So that's basically my topic. Zero knowledge proofs are not necessarily specific for blockchain, so I want to get that out of the way in the first step, because the applications that I will show are basically completely independent from blockchain. I will give some applications that are blockchain related, but basically everything that I'm showing here is independent from whether you're running a blockchain or not, right? So yes, here that works as well. So what are we going to see? First, a bit of, well, I've tried to strip the mathematics from the slides, but it's based on a lecture that I gave before. And so I tried to cut out most of the mathematics, but I'm very sorry if you have a math allergy, then maybe close your eyes now and then. Today I discovered I have a grass allergy, so if my enthusiasm drops during the presentation, I'm sorry about that. So first we'll see what is a zero knowledge proof, what are the properties that we want from a zero knowledge proof. Then we'll see what a zero knowledge proof looks like or how you can construct one. And then we'll dive into actual applications, right? So a zero knowledge proof is a system wherein the goal is to prove to someone else that you're being honest about some kind of a statement. That's a very broad definition that I'm giving there. Specifically, we're looking here at zero knowledge proofs of knowledge. Okay, so a proof of knowledge means that I can prove something to another party in some efficient kind of way that I have some knowledge about something. For instance, I know a certain private key and I can convince Shane that I know this private key, I know this specific number. A zero knowledge proof of knowledge it's more specific. It means that you can prove this thing without the verifier learning why this knowledge is true. So they don't learn anything more than the statement that you're trying to prove. This probably sounds a bit vague here, right? But an example is, for instance, and I think that's the next slide even, yes. An example is a cryptographic signature. So that will be the next slide. If you want to go into these details on this slide, these are the 3 properties that we require from a zero-knowledge proof. I highly recommend reading this the blog by Matthew Green here. You probably have heard about Matt Green. It's a very good illustration on the intuition behind these properties. So I'll quickly go over them. So the idea of a zero-knowledge proof is these 3 properties. So first you have completeness. It means that if the prover is honest, so if I'm being honest, then I can convince Shane about this fact. So that's a very basic property that we want from this protocol, right? If I'm honest, then the other party is convinced. The second property that you want is soundness, the verifier. So Shane will only be convinced if I'm being honest. So if I'm not being honest, the protocol fails. And then the third property is the zero knowledge property. Shane does not learn more than what I wanted to prove. So we'll go into a few details, into a few examples there. So the first example here is the mathematics. I'm sorry, you don't really have to see them. Sorry for my grass allergy, by the way. So the first property, the first protocol that you can look at is a signature scheme. And this is an example of a cryptographic signature scheme. And a cryptographic signature is in essence nothing more than me proving to you that I know a certain private key. So I have a public-private key pair. The whole world knows my public key, and I'm the only one knowing the secret key, the private key. And so a signature scheme is nothing more than just proving to someone else that I know this private key in the context of a certain message. So I didn't include the message in this transformation, but usually the message goes into this hash function, right? So the hash, and then you have the commitment K, and then you append the message over there. So that's how a signature usually works. So that's the idea behind the Schnorr signature. And so to set the intuition for the properties there, so the completeness means that if you verify the signature, then, well, the verification equation checks out. So the below equation checks out, if I'm being honest. And then the soundness means that if I'm being dishonest, I cannot generate this signature, right? And zero knowledge, well, you shouldn't be able to extract my private key from the signature. So in that sense, it's zero knowledge. Now, this is a very wrong way to tell you what a cryptographic signature is. All the people that do cryptography in here will probably try to shoot me, because you need completely different properties from a cryptographic signature than what you do for a zero knowledge proof. But they are very much related. So basically, you could say that a zero knowledge proof is a generalization of a cryptographic signature. Okay, so that's the basic idea. I hope that's more or less clear. There is some activity in the chat, but no, okay, that's fine. Yeah, okay, so here is the note. If you add this message inside the hash function, then you create the signature scheme. Okay, so now a question you could ask yourself is, what other things can I prove? Because this is a very simple proof of knowledge where I say I know a certain secret. And in the 80s, end of the 80s, there were mathematicians that have proven that basically every statement in NP, which is a complexity class, has a zero knowledge proof. And if you translate that from math speak, it basically means that you can prove arbitrary statements, if they are true, through zero knowledge proofs. So without disclosing the reasoning behind why this statement is true. But those people were mathematicians, and in classical mathematician sense, they said you can do it. They really didn't tell us how you should do it, right? So that's a very typical thing you see in maths. They prove that it's possible, and they don't tell you how. Or they tell you how, but it's not efficient, and things like that. And so only in the past 2 decades, I would say, we've seen very practical zero knowledge proof protocols, right? So let's say since 2016 or a bit before. And one of the, well, basically my pet peeve there was bulletproofs, which was in 2018. And here is the math allergy again. You don't have to know the equations for the exam, don't worry. So what bulletproofs did was they are known for a very specific thing. So the paper is known for a very specific thing, but they also popularized together with Grot in 2016 the idea of making very generic statements provable in zero knowledge. And so the way that they do this in case of bulletproofs is they model the statement that they want to prove as an arithmetic circuit. It's basically a circuit that says, okay, I have wires that contain numbers, and you can add numbers and you can multiply numbers. And with those gates, so addition gates and multiplication gates, you can make complex statements. And those gates you can model as this set of equations. So either the first set of equations or the second set of equations. And that's why there are formulas there. And to set the intuition behind those gates, it's pretty easy to see how those gates can be used to construct Boolean circuits. So if you have a Boolean circuit like your computer contains Boolean circuits, your CPU, for instance, you can transform those circuits into arithmetic gates. So for instance, if you have an OR gate, you have two Booleans, an OR gate, then, no, let's start with the AND gate, sorry. We represent a true value as 1 and a false value as 0. And then you can say, okay, if you have an AND gate, you multiply the two numbers. And then the output of this multiplication gate is the AND operation of those two Booleans, right? An OR gate is a bit more interesting. You can sum the values, but then if both values are true, then the output is 2 instead of 1. So you can basically, if you want to compute A or B, then you say, okay, A plus B, and you subtract A times B. And then you have an OR gate. And with all this logic, you can do 1 minus a value, for instance, then you have a NOT gate. And so you can build Boolean gates, which basically means that you can make arbitrary Boolean logic in this set of equations. And then you give this to those smart people of 2018 in the bulletproofs paper, and they can give you a zero knowledge proof about the statement that you just described. So after that, well, it was 2018. We're in 25 now. There is a lot of literature. Like the cryptographers had a lot of fun with these systems, and they improved upon these. And then at a certain point, we had the rank 1 constraint systems, which are simpler kind of an equation, and they allow you to have quadratic gates, basically. So instead of doing standard multiplications, you can also have squares of numbers, which can be more efficient in certain situations. But basically, we have different representations for the statements that we want to prove, right? Okay, and this rank 1 constraint system is probably one of the more interesting and important ones, because many different proof systems, so many different systems have been developed that can prove statements in this rank 1 constraint system form, right? For instance, 2020, we had Spartan, which came from Microsoft Research. We had Eli Ben Sasson, who made Stark, which is a transparent system. We have Nova, 2022. But there are also other constraint system formats. And so this became a whole ecosystem about what do you want to prove, what's the most efficient format, and all these families of proof systems started to appear. And then another example, most recently, 2023, and basically it's very recent because I've yet to see complete implementations of this, but the customizable constraint system, which is again a generalization, and so there's a lot of research happening there. So I think this is the last equation with the last slide with equations. Sorry. I think, yes. So a question you could ask yourself now is, I've been saying you can prove stuff, general stuff, but what exactly can you do there? And give me an example. For instance, we can go back to what Renata just was explaining to us, right? The self-sovereign identities, the verifiable credentials. So let's say we have this verifiable credential over here. We have an identity card, or we have my identity card. I'm going to hide my card number because otherwise you're gonna copy this. So this is my my Belgian identity card, and it contains this this chip, right? You have the IC, and so something you could ask yourself is, what is on this IC? What can you do with it? Well, turns out this contains a certificate, a digital certificate, which is signed by the government, right? And it says, okay, Ruben De Smet, you live in certain village, you were born at a certain point in time, the card is valid from, and so all the text information that is on there is actually in the chip. There is your picture is there, it's also signed, your identification number, and all these things are on this digital certificate. And so one thing you can do with a zero knowledge proof, and which is basically building on the verifiable credential idea from before, is you can take your identity card, put it in a big meat grinder, which we call a zero knowledge proof, and you can get something else out of there. And this something else could be any derived statement from your identity card. For instance, a piece of information that is not on your identity card is your age, right? Which is also what Renata said, like you can prove that you're over 18, which is extremely useful if you go to a bar and the bartender asks you, can I see your ID card? And you say, why? And he says, well, I need to check whether you're over 18. And then you say, no, I have a zero knowledge proof for that, right? So that's how you order beer nowadays, or how you should be doing it, because the bartender doesn't have any business with my name or my birthplace and all this information. And that is why zero knowledge proofs are interesting for privacy. And the nice thing is, with verifiable credentials, we have a standard, right? So we have standardized the format how to present certain credentials. But zero knowledge proofs actually allow you to take any arbitrary data, like the chip on your Belgian ID card, and even use this one to generate the zero knowledge proof. I'm not going to say that it is very efficient, but it's actually technically feasible and possible. And we actually have an implementation here in our lab that can do this. And so you can prove that you're over 18 years old, or any other derived data that you can imagine. So here some examples, some more examples. So Ruben, I prove that I have knowledge, some form of knowledge. I know about a certificate, that my personal data or my knowledge allows me to drink beer, which is a very general statement because it depends on what country you're in. If you're in Scotland, which is part of a country, of course, it allows you to drink beer if you're over 18. So part of the input to your zero knowledge proof should be where you're located at the moment. So you need to be over 21 over there. In Belgium, you need to be over 16. There are countries where you need to be over 18. So this all differs, and so you can make those statements. Another idea is I have personal data, my ID card, which allows me to vote. It's a statement that you can make. And all those things without revealing the original certificate. So without revealing who you are, where you live, and all those things. Because the certificate on your ID card, it only signs all your data at once, right? So if you give the certificate, or even if you give part of the certificate, you can't verify it. So you need to give the whole thing, and that's a bit the idea. Yeah. So another idea could be there is a database server at the university, and since I am a professor of a certain faculty, I can access parts of a certain database. But you don't even have to disclose your identity. So this is what makes makes the system self-sovereign. That's the SSI idea. Another idea, and this is more blockchain related, and this has been popularized, I think, in also 2018 mainly with bulletproofs back in the day, on Monero and with Zcash. They used zero-knowledge proofs to prove that a certain transaction was valid without disclosing what the transaction was about. So I prove that I transfer a certain amount of money, and I have that money, and I can transfer it on a blockchain. So I create a transaction, and I say I have this money, and I'm transferring it to somewhere else, and I'm not saying who I am or how much it is, but it is correct. So that's one way to use a zero-knowledge proof there. Another idea is privacy-friendly road pricing. I heard a week ago, I think it was back on the news, the Belgian government wants again to introduce road pricing. And so the idea of road pricing is that we have very congested traffic. I'm here in, my microphone runs away. I'm here in Brussels, very congested traffic. And the idea is we want people to drive outside of rush hour. And so we will bill people based on when they are driving and where they are driving. If you're driving on the ringway around Brussels at 5 in the afternoon, you will have to pay a lot of taxes. And if you're driving outside of this period, you pay less. That's the idea of road pricing. And so in 2008, there was already a proposal, and also in 2010, then it was really zero knowledge. There were proposals to do this with zero knowledge proofs. I prove that the amount of taxes that I paid complies with where I drove and when I drove. And that's the idea there. And one contribution that we did at our lab, which was part of my PhD, is you can actually make a protocol using zero knowledge proofs, which is less intensive on communication cost than just naively transferring or uploading all the driving data to a server. And so the number of elements that you have to send to the server is logarithmic in the distance that you drive. If you have to upload where you are driving, you have to upload the whole road trip, right? And so just as an example, I do have time for that, right? Yeah, I can still go a bit in there. So the idea here is we have 3 phases. So when you're not driving, the system is idle. Then you're driving a bit. So let's say I exit the campus over here, I drive left. And at the end of the day, the onboard unit, so the device in the car that's tracking you, sends a commitment to the tax server. And a commitment is basically a hash function. You can see it as a hash function of where you drove and when you were there, right? Commitment has some more interesting properties than just a hash function, but for sake of argument, it's a hash function. And the hash function you can't invert, so you can't know where you were driving, right? So you send this commitment to the server, and the server says, okay, great, but I saw you turn left on the General Jacques, so that means you have to prove to me that your commitment contains this specific point. And then you create a zero knowledge proof, and you prove that indeed, somewhere in the committed route, you passed that checkpoint. And so the government can test whether you're actually complying to this protocol. And then the government can accept this, and your device goes back to the idle state. At the end of the tax declaration period, at the end of the year, you declare your taxes to the government. You say, okay, I have to pay 12 euros and a few cents. And I prove that this is just just the computation that you did. So the computation for your taxes is consistent with the routes that you drove, with the committed routes that you drove. And in this way, the government only knows that you've been at those spots where they already saw you and the amount of taxes that you have to pay. If you put the system on a blockchain, then you can even say, okay, I paid the correct amount of taxes and I don't even tell you how much I paid. It's also possible, but we didn't go that far. But that should be possible in the end. Yeah, okay, so I made this interactive, oops. I'll make this a quick one. So this used to be a picture of my EU digital COVID certificate, but since this is being recorded, well, it contains all my medical data, right? So if you remember 5 years ago, the COVID certificate, it was a big QR code, and it contains a lot of medical data. It contains when you got which vaccination and all those things. So with the zero knowledge proof, you can actually extract all this data and then prove to the bartender that you're allowed to enter the bar because you had the necessary number of vaccinations, or you were tested, or you recovered, without disclosing which of the three options it was. So that's something you can build with the COVID with the ZKP. Yeah, so here you see what the certificate contained in plain text, by the way. So this is all plain text: names, date of birth, vaccinations, recovery, and then a signature of the government. And with the zero knowledge proof, you can just validate in the zero knowledge proof with this circuit the signature. You prove that the certificate is still valid for the day, and you prove that you're eligible for some certain activity for which you needed this COVID certificate. And you can implement all those things without even having collaboration with the people that designed the certificate. You don't need their consent for this because this is just mathematics and it just works. And then some final ideas. So maybe going back a bit to the blockchain theme. There are a lot of things happening in the space, in the zero knowledge space. For instance, we already had the example of the self-sovereign identities on Hyperledger with Anonkreds. It's really cool. I didn't know Hyperledger supported them, so thanks for sharing that. But something you see now on Ethereum, for instance, is the idea of a ZK rollup, where transactions are aggregated, and then after a certain period, when the transactions are aggregated, you prove you generate a more general transaction, one single transaction, and you prove that it is correct, so that this transaction is the sum of all the previous ones, and then you can compress them all in one zero knowledge proof, and it's actually more efficient to verify the single zero knowledge proof in a Ethereum smart contract than to actually verify all the independent transactions. So that's the idea of a rollup. You compress a whole bunch of transactions into one. And other things that are happening are VMs. So we actually have implementations of zero knowledge systems that prove the correct execution of a virtual machine. So you, for instance, have a RISC-0. So you can write Rust code, compile it to RISC-V, and then verify the correct execution of this Rust code using a zero knowledge proof. Yeah, many of these, many variants of this system are, or variants of this idea are popping up now. Another cool idea that came up is the embedding of a proof. So you can prove that you know about another zero knowledge proof. So you basically make a recursive statement. You say, I know a zero knowledge proof, which proves a certain thing, and therefore something else is true. And many techniques for that are popping up. Like initially it was the embedding of a proof, then it was proof carrying data. Now we have folding with Hypernova and with Nova. And a very interesting application of that idea is building a constant size blockchain. And that's what they were called Mina back in the day. They changed their name, so I don't really remember the name. It's O1 Labs. So they basically have a blockchain that consists of only the final block. And the final block contains a proof that says that all the previous blocks were correct, including the current one. And so the previous block contained another zero knowledge proof, but that means that the current block needs to validate that the previous zero knowledge proof was valid, and so on until the genesis of the blockchain. But that means that you only have to keep the final block, and everything else, all the other data, the transactions and the account values, they are gossiped around. So that makes for very interesting ideas. what does happen nowadays is zero knowledge proofs are usually in blockchain space usually used for efficiency reasons, because it's usually more interesting to verify a zero knowledge proof. It's faster than to do the actual transactions themselves. So that's something you see a lot nowadays. I think that was my final slide. So if there are interesting, oh yeah, I see some questions popping up. So difference between use cases for interactive versus non-interactive ZKP. Well, the thing with non-interactivity is online dating. Yeah, indeed. The thing with interactive zero knowledge proofs is usually they are constructed in a way that you need an honest verifier. And in the real world, your verifiers are usually not honest. So that's one thing. So usually what people do is they construct the zero knowledge system interactively, and then they use via Chamir to make it non-interactive. And if you want to make it interactive again, you can send the non-interactive zero knowledge proof. So that's usually what's happening, I think. But correct me if you have some ideas there.
We have time for one last question, as I saw one last one was dropped.
What's the? Oh, that's a lot of questions there. Yeah, there is certainly a link with Solid, but that's a very big story. Legal value. Oh, whoa. I think I'm going to take Wim's question there. What do you recommend for people wanting to start with zero knowledge proofs? So if you want to learn more, start with the blog post of Matthew Green. So that's a starting point. If you want to actually work with zero knowledge proofs, I think you should probably check out the RISC-0 project and the Kaleido project, because they're blockchain independent. And probably the ArcWorks proof system they have a lot of examples. I'm not going to say that they're very user-friendly, but they have a lot of examples, and you can find a lot of things there. So I think that would be my answer to that question.
Okay, and because I have the luxury of being the host and drop any question I want, I think also very relevant for everyone is you need to be a cryptographer to be able to make any sense of this and implement it.
I think currently, mostly yes, but it's changing, especially with the projects like Kaleido and RISC-0. These things are really changing. So nowadays, you don't have to build your constraint systems yourself anymore, which means that you can skip the nasty equations from before. But usually, you still need some cryptographic knowledge because you're basing yourself. So the example with the ID card, for instance, is I have a certificate such that certain predicates are true. And to understand the certificate and the way that you have to parse the certificate and to validate it, it needs some cryptographic background. But this is gradually reducing because people are building tools to work around these certificates.
Okay.
Including us, by the way. We're working on such things.
Thanks so much for your presentation, Ruben. I will have to stop my ignorance of zero knowledge proofs then, as there could be a reason I could do it. And actually, somehow the luck has. So in the first part, we heard about self-sovereign identity, and we hear a lot about zero knowledge proofs that were in there. And actually now the next speaker, final speaker of today, will be Peter Broadhurst, who is the co-founder and head of engineering of Kaleido. And Kaleido is deeply involved with the recent LFDT lab named Paladin. And so where the verifiable credentials mainly live off the chain, now we will also hear how to achieve privacy, where you can keep working with smart contracts, for example. Yeah, while also using zero knowledge proofs and maintaining privacy. But I will leave it to Peter to explain this. Thank you.
Thank you, Shane, and a great presentation from Ruben. We're going to cover zero knowledge proofs again in this session, but not just zero knowledge proofs. And we're not going to be talking about scale, which was really great summary, I thought, that you left it there. And that's where zero knowledge proofs have been so focused on the last couple of years with the evolution of layer 2s, etc. And we're not going to be talking about that. We're going to be talking about privacy. And we're going to be talking about zero knowledge proofs as just one of the different technologies. And we're going to be talking about application. And because I've been living in America too long, I'm afraid we're going to be talking about ZKPs. I'd love to be talking about ZKPs, but I'm afraid I will keep on slipping into ZKPs as we go through this. So I'm going to be talking about Paladin. Paladin is probably one of the largest code bases that came into being in LFDT over the last year, net new. It's a large project. It's a lab at the moment, and it's a combination of quite a lot of work over quite a lot of time, bringing together approaches to privacy, but particularly bringing them together around EVM. And in this session, I want to give you an overview of what Paladin is. I want to take you through some of the key things that it does. I want to give you a little bit of a demo. And then we have the opportunity, if there's time, to go deep and deeper and deeper and deeper into how it works. But I'd also like there to be a chance for people to ask questions as well. I'm going to start with what it is and why it exists. And I think it's really important to start with the fact that privacy is not a new problem. It's almost certainly not a new problem to anybody on this call. It's not a new problem in the DLT and blockchain Web3 space. It's existed as long as I've been working in the space. But it is still not the primarily adopted solution when you look at sort of Web3 and DLT approaches. It's not because privacy isn't important, but because the approach to privacy that's generally been used by enterprise adoption in particular over the years has been to say, well, if we just put all of the data in, and if we only deal with the data that can be shared we put it in a box, maybe we use a channel backwards and forwards between just some parties that need it, or we use a technology that doesn't have a shared ledger, in the bottom of it, but still achieves a sort of a way of agreeing on data or verifying execution, we can sort of not need to have a privacy layer on top of a shared ledger because we don't have a shared ledger. Or we've seen a huge amount of value being derived, probably more value for blockchain than anywhere else, in saying, well, actually, if we're all willing to let go, have pseudo-anonymity through just an address is anonymous enough, and we're willing to have transparent DeFi applications on public networks, we can get huge power and huge value through that compromise. And I think now really the rubber is meeting the road for real world assets, things like real money that is backed by financial institutions, things like bonds and fund units, etc. That the bringing together of privacy with shared ledgers, real shared ledgers, the time is now. And it's not that the technology is new, but the application of it is still hard and difficult. So all of that said, where we're seeing, and Kaleido works with lots of different blockchain technologies, but one of the reasons why we're so involved in this project, we put so much of our time into helping this project come into being, is that we're seeing a huge amount in terms of shared ledgers of adoption of EVMs. Those EVMs might be just shared between a few different parties. They might be a layer 2, which is using a zero knowledge proof rollup for scalability. They might be layer 1 networks like Ethereum, etc. All kinds of different networks. And there's a huge amount of adoption of these in the programming patterns of EVM. There's a lot of enthusiasm for it. But if you've got just more than one company working together on one of these truly shared ledger technologies, then privacy becomes a problem, becomes a barrier. So Paladin specifically is a project focused on taking any one of those EVM ledgers. It can be a Hyperledger Besu, or just Besu as it's called now, shared ledger between 5 companies. It could be any one of those ledgers, and it gives you the tools that you need on top of there to do sub-ledger privacy, to have smart contracts that work in a privacy-preserving way. And the reality is that's quite a deep stack of tooling. You end up needing a lot more than just a MetaMask wallet where you just have your keys and the blockchain looks after everything else for you, because the shared ledger can't have all of the data on it anymore, at least not in the open. It either needs to be encrypted and stored in that shared ledger, or it needs to be held outside of the ledger. And the things that you're doing in terms of signing are much more sophisticated. You're probably going to be using zero knowledge proofs, etc. So the wallet functions that you need to build are really, really quite complicated. And all of the client functions that are needed, a lot of these things you'd normally associate with blockchain nodes. Suddenly your wallet, your vault, your node, your private node needs to do all of these things as well. And there have been lots of technologies that have done this. Whole ecosystems that have done it in the past, even for EVM, technologies like Tessera and Constellation before that have done this with a narrow view. What Paladin's trying to do is to make that pluggable, to mean that you can take all the different approaches, and I'll talk about the approaches supported today and the reference implementations out of the box in this session. And this is a client that supports all of them. So rather than needing a dedicated technology stack for each shiny new zero knowledge proof that comes along, you can have a runtime that's pluggable and upgradable to support all of those. And we're also going to talk as we go through about harnessing the true power of this shared ledger, that lots of these different privacy preserving smart contracts using different approaches and different technologies and different cryptography can atomically interoperate because we're using an EVM. So that's what, hopefully a lot more of that will make sense as we go through the session here, but that's the high level of what this is trying to achieve. A flexible, pluggable, enterprise-grade engine for doing this privacy stuff on top of any EVM, not a dedicated EVM for privacy, but any EVM. And if you compare this to the approaches that there are out there, you'll see that there are lots of different technology stacks for privacy out there. But in general, they only address part of the problem. Some say, look, we're done because we've invented the cryptography and there's a proof system and here's the solidity. There's a smart contract. Others say, well, yeah, we've got an SDK for that. That's the whole problem. Not only have we got the smart contracts, but you've got like a zero knowledge proof toolkit that can work for that. But actually the full stack includes, who am I transacting with? How do I get the data to them? How do I trust this stack? How do I do key management? How do I run this at scale? All of those problems, actually that engine, that's often either you end up with a stack unique to one particular cryptography technology, or that's just not solved for you and you have to go and do it. So that boring plumbing work, that's what Paladin's about. And because it's boring plumbing, you have quite a lot of it, right? It's complicated. There's lots of it that's needed. Paladin itself, I mentioned, is a large code base. And there's lots of components that you just need before you can do anything in privacy. You tend to need a very sophisticated transaction engine. This is one of the heaviest lifting pieces of the code base, is a transaction engine that knows how to do all of the stuff that you'd normally need to submit public transactions at scale with high throughput, integration to key management, queues of transactions, all of that stuff, but also knows how to coordinate signature collection and proof generation and all of the other things that you need to do in these privacy preserving worlds. But beyond that, it needs also to have the ability to have registry of who am I going to be connecting to off-chain, the transports to be able to connect to them, integration with sophisticated signing that isn't just simple signing inside of the engine, but how do I connect out to HSNs? How do I do HD wallet derivation and factories of keys? How do I integrate with things like zero knowledge proof generation that needs to have the keys in memory when they run? So a big piece of it is key management. It has to be able to detect and listen to the blockchain, find out what's going on, reliably listen to it. So it has to have a whole block indexer inside of there at high performance, listening to the blockchain, detecting events in order, knowing about confirmations, working with public chains. All of that's got to be there in order for it to function. And then really interesting, and we'll talk about this a couple of times as we go through, it has to have a state store designed for managing data that isn't directly on the blockchain. Data that can be committed to, as Ruben was saying, we can have a commitment, a salted hash to that data. We can refer to it in a way that we can tie back. I know I have the data and I know it relates to that proof. So you need to have this sort of data store. So it's a lot of actual heavy lifting work. And I said it needs to be pluggable. And one of the things we'll talk about a couple of times is this idea that lots of different technologies can plug in. And we'll talk about the 3 different main categories of these technologies that exist across the whole ecosystem. And there's reference implementations for each of these. And we're going to talk about how these plug in. And they actually plug into a common box. We call it a domain. And it's a package of off-chain code, it could be any language, and on-chain code that works together in harmony. And if you pull apart any one of the privacy technologies you've heard of that works with EVM, you'll find there's always this pairing. There's some stuff that needs to run outside of the shared blockchain, and then there's smart contracts that run on that shared ledger. So this is a packaging piece of work, proven with very different technologies. Very interesting implementations of those to show that you can plug in lots of these privacy technologies together. So let's talk a bit about those privacy technologies. So what we've seen evolve over time, this isn't new for Paladin, this is kind of like what we've seen happen through so many different technologies, too many to sort of name, is there's actually a sort of pattern that's formed of, there are these things called tokens. They are incredibly important and powerful. A token is special because a token allows somebody to hold a record of something, usually a record of ownership, that they can prove to anybody through access to a shared ledger. So that means it's portable. You can take it, you can receive it from somebody else, and you can prove it. You can receive it from somebody, and you can prove it to somebody else. Very powerful concept. And there were a lot of privacy approaches that have formed for those. And I'm going to talk about the main 2, zero knowledge proofs and notarized tokens, that have formed for how do I hold something and then later prove I hold it to somebody else. These are a very, very different shape to the 3rd type of thing that exists, which is programmable, like blockchains in a box. Like for this audience, maybe fabric channels you might have heard of in the past, or avalanche subnets, or Polygon supernets, or layer 2 rollups. Blockchains that kind of have a separate world and kind of roll up to a parent. Well, this is what the technology that you might have remembered called Constellation, that became Tessera, part of the Quorum project, and then it started working with Vesu. It only did this model. And this model is extremely useful and extremely powerful. But what it allows you to do is it allows you to create little worlds, boxes, that are worlds in their own right. But things that go inside of those boxes get stuck in those boxes. So these things are great for workflow, for agreement, for backwards and forwards exchange, for programming a journey with a start, a middle, and an end, but they're not good for tokens. You cannot put a token inside of one of these, or it gets stuck inside of one of them. So technology stacks have usually given you one type of token. Maybe it's a zero knowledge proof stack. So you get, oh, brilliant, you get zero knowledge proof tokens and you can program them. Or you get like a notary model, and we'll talk about that in a second. That's what the tech does, is it just notarizes things, and the notary signs off on this, and it's good and it's great. Or you get something like Constellation Tessera. But actually, no one of those tools is good enough to solve the whole ecosystem. You need tokens of different types, and you need programmability across those. So that's why we say Paladin is about programmable privacy, because it brings these things together through the power of EVM. So let me, and I know I'm nudging forwards, but I'm conscious of time. So I'm going to keep on pushing forwards and try and make sure that I leave time for questions at the end. So I'm going to talk about these in a little bit more detail before we go and show them in action. And I'm going to start right to left, because usually when we're talking in the Linux Foundation about EVM and privacy, people are like, well, that's what the recently deprecated Tessera is about. That's what I'm expecting to hear about, is private EVM. So let's start there, and then we'll compare it to why that isn't the whole story. And we're going to start there, and we're going to talk about actually Paladin is the box that anything can fit inside of, and it's reference implementations. It comes with a reference implementation of private EVM worlds, and these are EVM worlds for privacy, not scale. So this is not about ZKEVM and all of that sort of stuff. This is about being able to have private EVM worlds. It comes with a reference implementation, which is actually a significant next generation of that over previous implementations. Called it Pente. The background of that is that Tessera is 4 in Greek, Pente is 5 in Greek. So you can see that Pente is a logical next evolution of that. And if you had some projects which were built on Tessera and you were worried about the fact that that model no longer exists, it's no longer supported, there's no one looking after it, it's no longer compatible with Besu in the next release, and you were thinking about, well, where do I go? Well, actually, Pente privacy groups are pretty much a straightforward next step for you. They support any EVM logic, and you just run it in a private box. But it works in a fundamentally new way. The thing that's really powerful about this is it's, rather than these being long-lived, heavy, cumbersome sort of things like channels used to be, like that have to be set up and live for a long time, these are ephemeral. Think of them like Lambda functions. We bring EVMs into being just to run a single transaction and throw them away again. If you want a smart contract to be deployed to your own private blockchain for one transaction and then to throw it away again, with Pente, that's pretty efficient. It's pretty efficient. That's not unrealistic. If you want a private world that just exists for you to run EVM privately, and you want it pinned to the blockchain, you don't really want to worry about sharing it with anybody else, but you want it to last forever, it fits that model as well. So it's a very flexible new approach, and we might have chance, depending on time, to come back and talk about how it works in detail. But this does use another really, really great Linux Foundation Decentralized Trust project called Besu. It doesn't use the whole Besu node. It uses the EVM implementation of Besu. And that means that any smart contracts will work on this. Any EVM smart contract can be deployed inside of one of these boxes. So that's just one of the 3 legs of the stool. Let's talk about the other 2 legs of the stool that sort of make a programmable privacy ecosystem. And that's the 2 approaches to tokens. And you can pretty much look at any token implementation that exists in any DLT Web3 technology, be it a Canton DAML implementation, an R3 Corda, a Hyperledger Fabric, or any EVM implementation, and you can look at it and you can sort of break it down into one of these 2 modes if it supports privacy. I'm ignoring the mode which is transparency, very powerful. I don't think it's a wrong model. Stablecoins using transparency for power, it's great, right? Like there's a scalability factor there that's really powerful. But if you want privacy on top of that, then there's basically these 2 models. And one is issuer backed. Everything that brings a new token into being is verified by a centralized or slightly decentralized party that is involved in every transaction and pre-verifies it, states this is valid. Yes, that token can come into being. And because they were involved in every token that ever came into being, everybody else who's just using those tokens can trust any token that exists, because they know no token could ever have come into existence without that party being involved in it. Think about a bond or a tokenized funds unit. There's some kind of regulated entity, a transfer agent, a registrar involved in that, and legally they have to be. So if they're involved in every transaction, and you know that they are, and they sign off on all the transactions, then anybody can trust that they received one. The transfer of it to them was signed off by that party. It feels centralized because it has to be. But that doesn't mean that the whole technology is centralized. It just means that transactions involving that one particular asset need to involve the issuer of that asset. This is the whole way that a lot of privacy technologies work. We talked about, I mentioned Downward Canton, I mentioned R3 Recorder before. This is like their fundamental model. Like, that's the model that exists. So Paladin supports that model, and we can see that in action. But there's this other model which is really, really powerful, and it's actually where most ecosystems want to get to. It's where they see their future of a zero knowledge proof. And here you don't have to trust any individual centralized party. You trust the maths. I managed to say maths rather than math. Usually I have to say trust the math for the American audiences here, but you trust the mathematics, right? You trust that nothing could have ever happened with this token unless a proof was submitted. And if you trust the mathematics behind that proof, you trust any token that exists because you trust the mathematics. And this is really powerful. So these are the two models of tokens. Neither of these can be programmed inside of one of those Constellation Tesla boxes, right? So, but you can program across these. So the power of having an EVM at the bottom is that you can atomically interoperate. You can have delivery versus payment and other multi-leg transactions where different legs are different models and they all complete as a whole or not at all. Right? That's the power of EVM that is the reason why it's worth the overhead of not having like a completely bespoke ledger at the bottom of this that isn't programmable because it just does one job. Is the fact that this level is programmable so you can implement each of these also means that it's programmable to interoperate across them. So that's one of the reasons why we see, it's not the only technology that we work with, but it's one of the reasons we see the desire to have shared programmable ledgers where the not meaning to be confused with base, the L2, any EVM sort of foundation ledger at the bottom can be used for worlds of interoperable privacy on top. So that was a lot of information. I'm probably going to try show it in action and then come back to questions, and we'll because I feel like a lot of the time seeing something makes it a little bit more true and easier to understand. So I'm going to move for a few minutes to showing you each one of those three legs, and I'm going to try and start in the same order that I showed them before. Not all of this is going to be UI because this is what you can go and do by downloading this project yourself and running it on your laptop. So that's a really important thing to say, that everything that I've shown you today, everything I'm talking about is part of the Linux Foundation. It's Apache 2, open source. It's a very large project, but it is a completely available right now today project that you can go and download. It's there as a lab. You can go and get an environment like this stood up on your laptop where you can have, as I have on my laptop, you can have 3 Paladin nodes. Think of them like your own private vault or your own private wallet. It's a data store. It's where key management happens to talk to the blockchain. But each one of these is like representing a node that's privately held by one party in the system. They're cross-connected by private data transfer. So they encrypt and transfer data between them, but they're all connected down to a shared ledger. And in this case, on my laptop, I've got 3 nodes, all Besu nodes. But remember, this could be any L2, any public blockchain you like. There's nothing special about these. It's just a Besu network that I've got running locally. It all gets stood up with a Kubernetes operator that comes out of the box. So there's a lot of cloud engineering that comes out of the box with this. It actually includes a Besu operator as well, because there wasn't a sort of lightweight, easy dev friendly one of those out there. So you get everything that you need out of the box to do that and deploy all the smart contracts. So the operator knows how to deploy all those smart contracts. So you run a couple of commands on the quick start through the docs, and you end up with all of this running on your laptop. You have 3 Paladin nodes, 3 Besu nodes, and all of the stuff deployed. And then you can run the examples. And the examples are pretty easy to run. I'm going to just run through a couple of them. And as promised, I'm going to start with a programmable EVM world, like a private EVM, just for 2 out of these 3 parties. I have, I'm sure anyone who's done 101 of EVM programming will have seen something like this, a simple storage contract. It just stores and retrieves values. It's a very simple contract, but it could be anything. I'm just using something simple. It just has a number, and you can store a new number, and you can retrieve the number. A very simple smart contract indeed. Written in completely vanilla Solidity. And I have a little script here, and what it's going to do is it knows about the 3 Paladin nodes that I've got. It knows about 3 users, which have been generated randomly, because Paladin's got all the key management to just like bring keys into being with the right key store backing it. It's using a HD wallet in this case. And I have a user on each one of those nodes. And what it does, if I just run it here, it's going to run against those nodes. It's got the identities. It's going to create a privacy group. You see here, new privacy group using the little TypeScript SDK. It's very simple APIs. These are JSON RPC APIs. You don't need to use the TypeScript SDK. It's going to create a privacy group. This is actually creating a blockchain. So it's saying things like, what EVM version would you like to use? And how does the endorsement work? I don't feel like we're going to get to the full details of what endorsement means. But like, what's the model for this little blockchain I'm going to create? Right? I created a whole blockchain just then. And I'm going to, inside of that blockchain, I'm going to deploy a smart contract inside of that blockchain. But the blockchain's only visible to users 1 and 2. And then against that blockchain, I'm going to run against the smart contract that I deployed from the bytecode that was compiled earlier from simple storage. I'm going to send a transaction to it to set the value to 42. Right, that's what happened down here, and it got a receipt. You can see it's got a transaction hash. Everything you do in the higher levels, like the privacy layers, is a blockchain transaction. A lot of the times, one of the criticisms of blockchain technologies is that they're not really privacy technologies. It's not really using the blockchain. Everything in Paladin is really using the blockchain. Almost everything in Paladin is actually using a UTXO model on top of the blockchain. Too much detail to go into for today, but the vast majority, it's probably like an 80-20 rule that you find privacy technologies, whether EVM or otherwise, tend to use a UTXO model, because this idea of states that are indivisible in their own right is very friendly to privacy, because you can have different people having different ones of those states. Whereas if you have like an account, to have any interaction with it, you have to see the whole account. So UTXO models tend to be the one that is used. But all of these different technologies, whether it's these privacy groups that I'm showing now, whether it's tokens in Paladin, they tend to use a UTXO model. Just a time check here. I think I've got a few more minutes. I'm just going to try and zip through to the end of the demo and pause for questions. But this setting of the value, what I want to show you is I'm going to go across the user experience of Paladin that comes out of the box. And I'm going to show you those 3 different nodes here. If I can get Zoom to disappear out of the way. Okay, thank you. I've got 3 different nodes, and we said we've got node 1, node 2, node 3. And we said we ran a transaction on a blockchain kind of only visible to node 1 and node 2. But the transactions are on the shared ledger. So what do we mean? Well, I mean, if I go to node 1 and I have a look at this transaction, you'll see I have lots of details about the transaction. Importantly, I can actually see inside of the transaction that this was a store operation against a smart contract to store the number 42. And I said there was a UTXO model. So if I go down to the state receipt, I can see that actually there's a whole bunch of spent states and there's a whole bunch of confirmed states. For those who are interested, each of these states that get spent and used are actually the addresses in the accounts in the Ethereum little blockchain. So the externally owned accounts with just nonces inside of them, the accounts that have got code inside of them, each of them is modeled as a UTXO state. If I go to blockchain, go to Paladin node number 2, and I look at their private view, I can see the same. I can see the number 42. I can see all of that data. How? Because through the process of submitting this transaction, all that data got shared from 1 to 2, and they both endorsed it. They both signed off on the outcome. If I go to 3, though, I can see the transaction. I can see it happen because I can see the shared ledger. I can't see very much about it. I can see that there was one. I can see the hash. This is what's actually on the blockchain, right? Commitments to states. I can see some states appeared and some states got spent. I can do a little bit of metadata analysis on this because I can see trees of transactions, but goodness knows why somebody was submitting them to this smart contract, what the smart contract actually was inside of there. I can just see the existence of the blockchain sort of there, and I can see stuff happening, just like in the past. But I can see inputs and outputs, which means the proof of execution was there for each of these transactions. So that's kind of one model, and super fast. Maybe I'm going to skip the notarized model because it's the least interesting of the three, and I'm going to zip through to tokens with zero knowledge proofs, right? Well, how would this look with tokens with zero knowledge proofs, the super powerful version? Things are a lot more complicated under the covers, but remember this is tokens now. So anybody should be able to in the future prove the existence of something. This isn't running inside of a block of like a private blockchain. This is natively running directly on the blockchain because the proofs are going to get verified on that blockchain. And I am going to use a little user experience for this, but I have some crib notes to make sure I get it right. So I'm going to go across to here, and I've got these domains are named our reference implementations. There's notarized tokens, Noto. There's zero knowledge proof tokens, Zito, and there's privacy groups, which I mentioned earlier was called Pente. I've got all of those locally, and inside of there you can have lots of different smart contracts, as you would expect. I'm going to pick one that I've sort of set up ready, and I'm going to do a transfer, and I'm going to do a transfer from a party who I know's on this node number 3, right? They're called Central Bank. This is coupled to a whole bunch of keys under the covers, but there's a nice naming system for the keys, like friendly naming system. And I want to transfer the data to the bank 1 identity, which is homed on node 1. So there's a registry to transfer the data, etc. there. There's lots of variants of zero knowledge proof tokens available out of the box with Paladin. I'm going to use one which holds the data off chain rather than encrypting it on chain. I'm going to transfer 1,000 units. And I do that, and we see another blockchain transaction appears here. If I look inside of this, I'm going to see it's zero knowledge proof, so it's a heck of a lot more complicated, right? That's probably if you wanted to know what's the TLDR of zero knowledge proofs, everything you do is a lot more complicated. And actually under the covers, what is dealt with here is that there is actually 2 very simple commitments. One is of new coins that came out of this. One is a new coin worth 1,000, which has gone to this owner. This is actually a baby Jub private key for those who are interested. There was some Circum stuff that ran using Peterson commitments and ZK Snarks and baby Jub encryption, to prove signatures inside of the zero knowledge proof. But I ended up with 1,000 going to one party, and then this thing is change of what I had left from the coin that I picked to spend. So a UTXO coin model. So Zito implements a UTXO coin model, and then there's all this other stuff because there's all these Merkle trees that have to be maintained, and Paladin lets you maintain those. If I go to Bank 1, which received the coin, they have a slightly different view. They can see most of these states, they can see the 1,000, but you notice they can't see anywhere on this list. They can't see the amount of change that the other party held back. They only see the coin that they received. None of their business how much change went back to the person who had it. And you see down here, there's a couple of the states were unavailable. It saw some of the transaction, but not all of the transaction, because only some of the data was transferred to it, or available to it because it was encrypted on chain. So that's a slightly different model. And if I go to the third node, who had no business in the transaction at all, because it's purely on the blockchain, they still have a whole bunch of stuff that they did. Why? Why? Because in zero knowledge proofs, they have to update all of their Merkle trees to deal with building proofs based on the new world state. So they still need to update their Merkle tree, but down here, they've got no idea what actually happened in the transaction. They just know how to sort of do this complicated off-chain stuff to continue to be able to follow along and create new transactions. Man, I'm sorry, that was quite compressed, and there was a lot of information there. I really am going to pause here. I'm not sure how we're doing for time, Shane, but maybe it's worth thinking about some of the questions that we might want to go back over some of that information.
Yeah, I'm sorry I gave you such a limited slot for such a huge code base. But it's nice to see it aligned with the other topics. And it's already 8:45 in Belgium time. But you're the last speaker, so I think we don't need to hurry with the questions. So maybe I think you can check if there's any question in the chat still left. If not, I can also ask one.
Yep.
There's no more question,
No
Patrick?
question.
Okay, then I will ask one. So I think until now, a lot of the privacy solutions for enterprise-grade use cases, I think were often not good enough. If I remember well, the Sarah was not scalable enough, even for some contexts. Do you think with Paladin that now there's like a milestone reached, or do we also need the Greek number of 6, 7, 8, and 9, which I don't know in Greek? Yeah.
It's an excellent question. The main challenge with Tessera was not how hardened it was. Those problems could have been solved. It was that it didn't solve enough of the problem. That was the fundamental problem with it, is it didn't solve enough of the problem. And I think what we have right now is lots of points. We've had a lot of experimentation, maybe experimentation into pilots, maybe whole ecosystems that have come and gone in a lot of cases that took a particular model that was limited. And what's different about Paladin is it doesn't claim to have all of the answers. It claims to be somewhere which is extensible as new answers come along. So I think that's one of the things that's genuinely different about Paladin. I think the other thing that's genuinely different about Paladin is down to this slide, which it tries to tackle the whole of the problem. And I think there's this huge amount of innovation happening in layers of cryptography and SDKs, etc. But actually for adoption, you need the wallets. You need if people want to hold stable coins at scale that are privacy preserving, then we've got to find the ways to have the technology that lets people hold them, exchange them, interact with them. And we need that to be interoperable with DeFi ecosystems, with other privacy technologies. So if we don't have some standardization, we don't lean into great things like open source, great communities like the Linux Foundation and LFDT to do this, we'll just have so many silos where it's great, you can achieve privacy if the only thing you want to do is your thing, but we need minimum viable ecosystems. We need stuff that works together. So those are the things that are passionate for the Paladin project. In terms of is Paladin done and it's completely complete? No, but how will it get done? It will get to being more complete through adoption and proof in fire, right? If you think about Ethereum as an ecosystem, that's how it got there. So the more projects that use it, the hardened it will get. What's that journey look like? How many years is it? I don't know. Is Paladin the only thing? I'm not sure it is. Is Paladin something that's quite open and flexible and designed for enterprise? Yes. Is it somewhere we'd love to get collaboration and innovation for real production projects? Yes, and it's already happening. There are some interesting projects, GWN, a few. I've got the mental checklist of which ones I can mention directly, but there's a number of projects that are actually actively using this for real sort of enterprise use cases right now today. It's not just on the shelf sort of software. It's actually being really, really tried for real things. So that's a long answer, but great question, Shane.
Yeah, it's a great answer too. Thank you. I saw a question here. Is this production ready? But I read between the lines that everyone is welcome to start testing it and that it's already being used in production. And maybe my last question for you for today. I think in the past, many people looked to private permission blockchains like Hyperledger Fabric with the private data and the channels as the only way to manage somehow privacy and using a blockchain. Do you think this will take away a lot of the use cases for Fabric? And what kind of use cases should I keep looking to Hyperledger Fabric for? I hope it's answerable. Thank you.
It is. Well, let me take the pattern first, right? The pattern of a genuinely shared ledger. Fabric has genuinely shared ledgers. Lots of things don't. Each channel in Fabric is a true shared ledger. Everybody gets a chance to execute those and validate those transactions. So it's a true shared ledger, as opposed to the ledger just being like timestamps, and the real stuff happens elsewhere, right? So that's a really good thing about the Fabric approach. Fabric channels, though, there was a time where the approach was to say, if we have a new privacy scope, we need a new channel. And a few years ago, there were projects that tried to say, well, we're going to have 20 participants. Well, that means every group that has like a scope of data needs a separate channel. And it's an n times m problem that gets super, super complicated. Well, Paladin takes the approach of saying, well, that's great, you can have those, but it can be millions rather than just tens. But don't think it's the whole solution. That channel is not the only way that you're going to want to interoperate, because if everything that you do between two parties is on a channel that's just got you and me inside of it, then none of the data that's stuck inside of that channel can ever be reused elsewhere. You lose the ability to do things like tokens, right? Tokens don't fit that model. You can build tokens in Fabric, but you can only build tokens in Fabric if you've got a shared channel that everybody's using. Now, the question of whether Fabric is the right ledger for you, or one of the EVM rollups is the right ledger, or would you like to write chain code, or would you like to write EVM, or would you like to write EVM that compiles down to chain code? I'm kind of not going to get into those because they're not really related to privacy. They're related to all of the other characteristics. But if you're using Fabric, you're probably using a shared ledger, and that's a really good thing to be looking at.
Mm-hmm. Great. Thank you so much, Peter. Thanks so much. I think we can, now wrap up the event. Everything has been recorded, will be published on the LFDT YouTube, so we can have maximum reach for this event. Also, all participants normally registered through their email address on meetup.com. So we will provide if you can also send to me, Renata, and Peter the slides, then we will, and if you have useful links or resources, we will email it to everyone that participated here. And then I think we can wrap up this event. So thanks so much to everyone. Thank you.